Good morning. Am I audible? Okay, fine. The first thing I'd like to do is tell you what I'm actually going to be talking about. I think I'm supposed to talk to you about this curve and that fitted line. What you see here are sea level data. This axis is not open, it is in millimeters. So all you need to look at is the axis for each particular curve. You have stations from the west coast of India and Pakistan and Yemen out here. This is from the Rainfall Sea on the east coast. Right now you have Visakhapatnam and Rainfall from the east coast. Now you see sea level variability. These are monthly mean sea levels that archived at the Common Service for Mean Sea Level. And they're based on tide gauge records. Not looked at much today, but they're only useful records if you're talking of long-term changes. The only other source of information on sea level is the altimeter, and that's just over 2 decades old. So I think what I was actually supposed to speak on is this line that is fitted. It's a straight line fit to the data, showing a trend, the rise in sea level. But I have no expertise in that business, so I'm not going to speak on that. Instead, what I will do is tell you what happens, what you need to know if you want to make sense of this curve. And that's the only reason I happen to be an author on this paper. It's not for this line. It is basically for how to interpret what is all these other things. And you really can't make sense of this line if you don't know what else is happening with the sea level record. In fact, if you want to understand sea level rise, you need to understand tides, and you need to understand very long-term changes. So it's a spectrum of oceanography that I would like to cover. So this is just a slide that we will come back to at the end of this talk. Okay, so what am I going to do? How many of you have no background in oceanography? I guess it is a pretty large number. Great. So a talk on sea level rise would have been almost useless, and I'm glad I'm skipping that. So I'm going to start by looking at the global ocean. What is the observed surface circulation? All I need from you is your attention and some recollection of what you learned in school geography and high school physics, nothing more than that. So we look at the observed surface circulation, we look at what's called geophysical fluid dynamics. We'll take a quick tour through that. We look at the theory that's been developed to explain what we see in the world oceans, and then I'll summarize that. Then we go to the Indian Ocean. We look at the forcing for changes in the Indian Ocean that's coming from the wave. We look at the surface circulation in this region. Then look at the theory that explains it, and we'll summarize it. Those who forget history, the content repeated. It's a very long path, and I'll take you to just 50 years of oceanography of the Indian Ocean in a few minutes. It's very intimately tied to what happened in other basins, but it's never taught in our colleges. And that's why I thought I'll keep this here. And then a quick look again at climate and sea level. But once again, from a very different perspective, if you want to understand that line that is fitted, and that line, its slope, is the only number with a plus minus error bar that's quoted in all these climate change reports. If you want to make sense of that, this whole thing is something you need to understand. So let's go. So the observed surface circulation. This is what the oceans look like, two different views of the globe. This is the Pacific, occupying almost 50% of Earth's surface, and the diametrically opposite view. If you take the zone, that is the east-west distance across the South Indian Ocean, around 15 south, it's about 10,000 kilometers. The Pacific is half the globe, so about 20,000 kilometers. The North Indian Ocean is smaller than the South Indian Ocean, and the Indian Peninsula, which plays a very critical role in determining the dynamics of this region, splits it into two smaller parts. So if you take the zonal distance across the Arabian Sea at 15 knots, we are talking of 2,000 kilometers. Not seen in this picture, but actually plotted out here is the depth of the ocean. So these are bathymetry contours. The average depth is about 4 km. This is something to be kept in mind. We are talking about horizontal length scales of the order of a few thousand kilometers and depth scales that are of the order of a few kilometers. This is a vertical cross section of the ocean, but exaggerated and magnified for 20 times in the vertical. So you have depth here in kilometers and distance from the shore. So you start from the coast, you go out, and what you find is that the depth changes very gradually. Typically is 100 or 200 meters water depth, after which it plummets. So this part, where it changes gradually from the coast outward, is called the continental shelf, and this part where it plummets is called the continental slope. Then you have slightly less steep increase in the depth, it's the continental rise, and then you have the abyssal plain. But it's not a flat bottom, even the abyssal plain. You have oceanic ridges, you have mountains, all kinds of things out here, even in the abyssal plain. What has to be remembered is that it is exaggerated by a scale of 20. This is from the Oxford School Atlas, which is what I used when I was studying in school. And I hope you remember this picture. It's a very simple view. So you have temperature and ocean currents. Let's forget the temperature. This was the Atlantic and the Pacific, unfortunately, is split into two parts. What you see here is gyre. The gyre is a closed circulation. Okay? So you have the Gulf Stream, the most famous of the western boundary currents. You have the Atlantic Ocean, this is the eastern boundary, and the American coast forms the western boundary. So you have the Gulf Stream, you have the North Atlantic Drift. So the Gulf Stream takes warm waters from the tropics towards the mid-latitudes, and then the North Atlantic Drift takes it right across the North Atlantic into Northern Europe. And that's what makes Britain habitable, while this part of Canada on the other side is almost uninhabitable. So you see population density that is pretty high on the West European side, while on the other side in Canada, it's much less. And the major cause is North Atlantic Drift, taking warm waters across. It seems to be close on the eastern side by what's called the Canary Current. And then you have the North Equatorial Current flowing westward and closing the loop. This pattern repeats in the South Atlantic, in the North Pacific, in the South Pacific, and the South Indian Ocean. The North Indian Ocean is different, and that's why we'll come to that later. But this is a very simple picture. It turns out that if you look at it a little more carefully, it's a little different. This is from textbook, and it's not very different from what Tessin Patel held in his hands in Life of Pi. It's almost the same kind of map. If you look at it, the Atlantic here, the Gulf Stream is still there. You have the Canary Current, you have the North Atlantic here, and you do have the North Equatorial Current. But it's not as if what goes north from the Gulf Stream comes down south from the Canary Current. You have the Gulf Stream flowing forward from equator to pole. But if you look carefully, you find that the return circulation is distributed across the entire basin. So you have a poleward flow of the Gulf Stream that seems to be compensated by equatorward flow that's spread right across the Atlantic, North Atlantic. And the Canary Current just happens to be swifter than most of the rest of this flow. The pattern repeats. You go to the North Pacific, the South Atlantic, the South Pacific, and the South Indian Ocean. So the Gulf Stream, and in the Pacific you have the Russia flowing of Japan. These are called western boundary currents. You still have a close circulation, it's called a gyre, and it's in the subtropics. The central latitude would be about 25 25 to 30 degrees in any of these systems. So you find a similar pattern in 5 basins covering a pretty large area of the surface. How did we put together this kind of picture? One source of information is what is called shift loops. No longer possible today because of satellite-based navigation. But if you put your mind, take your mind back, say about even 30, 40 years, when you didn't have satellites, the only way for the captain to navigate a ship out at sea was with what has been available for centuries, the sun and the stars at night. The sun, very often you lose it. If you have clouds, the same holds true for stars. But suppose you have a clear sky. The captain makes a fix, he gets his position. He gets his position and he knows roughly where he wants to go. So he marks another position on his chart and he sets what is called course from point A to point B. Now he is likely to get his next fix after several hours. So in the meantime, as the ship sails towards point B, it is deflected off course. And research shows that though 10 to 30% of this drift away from the coast comes from the winds, the effect of winds on the ship structure, the bulk of it can be explained ocean currents. So this drift away from the destination had been recorded for several centuries. And it is this shift that is one of the primary sources of information on surface circulation of the world oceans. The other source of information is something which is more intriguing. It is what's called hydrographic data, which is basically temperature and salinity profiles. These profiles started being collected from the 1870s onward, when steam power became available. Now, if you want to make measurements in the ocean, you need to be able to send some instrument down, but then you need to be able to get it back up on deck. And until steam power became available in the 1870s, this was not possible. With steam power, you could run a winch, a motor, and send down either a bottle or some instrument, make a recording, and bring it back up. So you could collect water samples. And very clever designs led to what's called a reverse thermometer, so that if you made a measurement of temperature at some depth, and thermometer basically reversed and locked it, so that even when you brought it up through warm waters, it didn't matter. The temperature was recorded at the depth at which you had made your measurement. These profiles have been collected ever since the Challenger expedition of the 1870s. It was a 4-year expedition financed by the British government, and it started what's called modern oceanography. So over a century and more now, temperature and salinity profiles have been collected by oceanographers whenever they go out. No matter what your field of interest, this remains a cornerstone. It's done even today. Probably more automated than it was earlier with what are called Argo floats. But the game is the same. It's to make a measurement of temperature and salinity and get a recording of the vertical profile. How it helps you in getting a current is something we'll come to after a while. But this is the only other source of information for the bulk of the world oceans. So what are the major features that we have seen? The first is semi-permanent subtropical gyres. Gyres, close circulations. Subtropical, because they're not in the tropics. The southern boundary of the Gulf Stream is around Florida, which is already around 25 to 30 knots. So you're talking of a circulation that is not within the tropics of Cancer and Capricorn. It is permanent in that the direction of the Gulf Stream does not change in time. It always goes poleward, towards the pole. It is semi-permanent in the sense that the magnitude of the current associated with the Gulf Stream can change with season, with year, maybe within a season. So this is the most striking feature of the circulation of the world oceans, semi-permanent subtropical gyres. These gyres are marked by intense forward western boundary currents. So the western boundary of the ocean, eastern side of the continent, eastern boundary of the continent. The currents flow forward and they're intense. Gulf Stream is in the Atlantic, Kuroshio is in the Pacific, North Pacific, and Nagoya Current is in the Southern Ocean. You have the Brazil Current and the East Australian Current as the other two major western boundary currents. There's equator flow at the eastern boundary. It's much bigger in comparison to the western boundary current. But this return flow that is equatorward, and that's needed to compensate for mass, you can't accumulate mass at the poles, is seen right across the basin. So it's almost as if you have a delta function western boundary current, and you have a return flow that extends all over the basin. The other thing that is seen in the data is a strong return flow just to the east of the western boundary current. There's an equatorial current system. You have the north and south equatorial currents and an equatorial countercurrent. There's also a very remarkable feature called equatorial undercurrent. A very thin wide by the standards of the globe, just a few tens of kilometers wide current that you can track right across the Pacific. Just a few tens of kilometers wide, maybe 100 meters or so deep, and the stencil stretches right across the Pacific, from one end to the other. You also have the only current that goes all the way around the globe, the Antarctic circumpolar current. So any theory that you build has to be able to explain these features. If you look at a vertical section of the Gulf Stream, here is depth, and you have offshore distance, this is 1,000 kilometers, and this is the east coast of the United States. These are temperature contours. And at the surface here, the temperature is of the order of 8 degrees Celsius, or 10 degrees Celsius, and that water is coming up from about 1,000 meters deep. This is called a filling. You have cold waters being fed to the surface. So this is about 10 degrees Celsius, the slow water. You have the Gulf Stream here, the core of it, and then you have the warm waters further offshore. So you have a very strong temperature gradient across the Gulf Stream. So this is a very deep flow. Its vertical extent is greater than 1,000 meters. Its transport, when you integrate it from the coast outward to the outer limit of the Gulf Stream, and in the vertical, over the depth extent of the Gulf Stream is of the order of 150 Sverdrups. Sverdrup is a unit named after a famous Shankar called Sverdrup from Norway, and one Sverdrup is 1,000,000 cubic meters per second. So it's 150 million cubic meters per second. That's the transport of the Gulf Stream. But if you look carefully, and this was possible through satellite data, at the Gulf Stream and the horizontal, you find that's not a very smooth flow. It shows rings. There are rings that form, there are meanders, and then you have vorticity. It's a remarkable field of vorticity that you see in the Gulf Stream. So this is what those temperature profiles that have been collected allow us to do. They allow us to map what happens across a current. And it is this kind of behavior, this affairing, and its counterpart, when isotherms dip down or downwelling, that we shall see can be exploited to look at what is the transport. When we give this figure of 150 Sverdrups, it's based on these temperature and salinity profiles. So you're actually using data of scalar variables like temperature and salinity to get an estimate of the current rather than transport associated with that current. So there is a similarity in circulation patterns, and if there is a similarity, it means that we must have a single theory that can explain them all. So that's the next step, and that's called geophysical fluid dynamics. Before we get to geophysical fluid dynamics, what's fluid dynamics? Two laws are of interest to us. One is conservation of mass, neither created nor destroyed, and the other is the second law, which simply put is rate of change of momentum is equal to the applied force. So that's all we are going to be using. The problem is that Newton's law applied to a point mass, solid body. And if I were to throw this, it has an identity and you can track it in space. So all you do is draw a force body diagram. You look at it in flight, you draw the force body diagram, and if you are given the initial conditions, you can compute the trajectory. You can compute everything. So it applies to a point mass, and Newton built his entire theory for solid body dynamics. But that is not the way a fluid behaves. In a fluid, there are certain differences that we have to account for. One problem is that if I were to take a steady state system, okay, there's nothing changing in time, and I have a flow with a gradient. Let's say I have a certain temperature A at 180, T1, and a certain temperature T2 out here. And I have a flow from T1 to T2. When the parcel of water moves from T1 to T2, its temperature has to change. Now this is not something you encounter in solid body dynamics, because in solid body dynamics this is an entity. With fluids we no longer have entities. We define entities in what's called a continuum. And one way to study it is to track that parcel that we define. But that is not the way we make measurements in a fluid. The way we make measurements, whether it's a piston engine or the atmosphere or the ocean, is the same. You put a probe at a given location and you're measuring whatever happens there in time. Like you want to measure the temperature in the engine, just have a probe out there, a thermistor, and it's recording temperature over time. That's the time series that you get. You can put multiple probes. What you will get is the field. So we are making a transition from a point mass moving in space and time with an identity that is clear to a field, and that is fluid dynamics. So the laws are, the law of Newton has to be looked at in a slightly different way, and this remarkable feat was achieved by Leonard Euler in the 18th century. It was almost a century after Newton that his laws were finally applied to fluid, and that was without friction. It was almost a century more before friction could be handled, and it remains today probably the only unsolved problem of classical physics. As put by Kelvin in 1889, there were two problems that were left in classical physics: black body radiation and turbulence. Planck took up black body radiation for his thesis. In 1901, the face of science changed with quantum theory. Turbulence remains to date a problem that has not been solved. And that is intimately connected to the way we handle friction. So it's still a problem that remains. We have ways of looking at it, and we get by. But yes, of interest to us here is just this. We're going to use two laws. We're going to apply Newton's law, which was built for solid body dynamics, to a field, so fluid dynamics. What is geophysical fluid dynamics? When you take a piston, or you take an airplane, or you take any flow that you're going to encounter in engineering systems, you never get anything that is like this tank. If you have depth and length as the two parameters of interest of this tank, then what you see here is an actual measure of the world oceans. You have an aspect ratio, depth to length, of 10 minus 4. If the length of the ocean was the length of this line, the depth of the ocean would be the thickness of that line. So we are talking about a flow that is remarkably different from anything that you encounter in classical fluid flows. But with one remarkable difference. If you were to look at flows that are so thin in engineering, and if you've done fluid dynamics, you would have done the experiment called Hinshaw flow. It's highly frictional flow. You have plates very closely spaced, and the entire flow is governed by friction. You have a balance between inertia and friction. While this flows, geophysical fluid flows, and we're going to be looking at them, we're going to be looking at invisible dynamics. So in spite of this low aspect ratio, very low depth to length ratio, you still have near interstellar flows, except near the surface and at the bottom of the ocean. So it's a very thin fluid that we're talking about. Very low ratio of height to length, roughly 1 to 1,000. So it's a very low aspect ratio. This has to be kept in mind when we study geophysical fluid flows. Doesn't stop there. It's on a sphere, and if you are looking at the Pacific, you can't ignore it. It's half the globe, so you can't assume that it's flat. It gets worse because the sphere rotates on its axis, and you have a non-inertial frame of reference. You could very well assume that the frame of reference is inertial if you were to park yourself somewhere else, say someplace at star. But unfortunately, you make all your measurements on the Earth, and you want your access with respect to that. So this forces you to look at a non-inertial frame of reference, and the force of hindrance that comes in, the pseudo force, is the Coriolis acceleration. It turns out that for flows that take more time, that is, their time scale is longer than the time taken by the Earth to rotate on its axis, the Coriolis acceleration dominates the momentum balance. So this is something you will not encounter in engineering. You take an airplane, the time taken for the air to cross the wind is a fraction of a second, and you don't care about the Earth's rotation. A piston engine or any of these things, you're designing an automobile, doesn't matter, the rotation of the Earth. But here you can't ignore it. There's also stratification. Now in oceanography, we are lucky that stratification is generally stable. In the atmosphere, the higher temperature is below, and when you heat from below, air rises and forms clouds. That's unstable stratification, and it can be extremely unpleasant to handle mathematically. In the oceans, we are lucky. Stratification is stable, you have lighter fluid overlying heavier fluid. But the nature of the flow depends on the scale. So here you have a plot of, this is the time scale. Sorry, it's pretty bad, it's difficult to read this. This is the time scale in days. It goes from 0.001, so 10 power minus 3 to 1,000 days out here. It's more than 5,000 days. And here you have the length scale in kilometers. It goes from 0.1 to a few thousands, 10,000 kilometers. Both are logarithmic scales. So what are the kind of motions that we see in the oceans? One is out here. There are two of them, two lines, very precise lines that are marked. These are the tides. The first one is a period of about half a day, that's the semi-diurnal tide. The period of 12 hours and 50 minutes. And the one here is the diurnal tide, period of 24 hours. Can't ignore them. These are the only two that really stand out as lines. We have one more line here. It's coming because of the rotation of the Earth. It's called the inertial period. It's strongest line because at a given latitude, you have a given inertial period. But this changes with latitude. The inertial period increases as you come close to the equator. You have one more boundary here, that is stratification dependent motion. This is called the Brunn-Weisel frequency, or the period here, and that's during delta days. You beat the ocean on the surface by any means, wind. It's going to set up oceans that can extend in frequency from the Brunn-Weisel frequency to the inertial period. These are internal waves. So this entire region is the internal wave regime, and you have the tides embedded within that in Germany, because the inertial period can go below a day as latitude increases. It will come close to that actually. So, okay. It's pretty poor here, but if you look carefully, this is the boundary here. these are what you see when you go out to sea. These are wind waves and swells. So if you go out to sea and you look at the surface of the sea, you see two kinds of waves. One is very regular and is driven by waves from a long distance. So you have storms in the South Indian Ocean. It can create what are called swells that travel a long distance, and it will have an impact on your ship no matter where you're sailing. They have a slightly longer period. Then you have higher frequencies and shorter length scales that are the local seas. That's what they are called. By the local wind. You have the wind blowing, you have your ship, and it sets up motion on the surface. So this is what you normally see when you go out to sea. You have the tides, you can see them, just go to a beach and sit there for a day and you will see the water coming in and going up with the tide. You have the initial period, and out here, the extreme top right, is what's called the global thermohaline circulation. You have water sinking in the north and south pole regions, and they sink to great depths. They move along at those depths, and they have traveled in other places, the Pacific and the Indian Ocean. So that's a circulation that takes several centuries. So if you were to manipulate something in the North Atlantic today by, say, warming it up, the impact is not restricted to your lifetime. It's going to extend for several centuries. And these are scales that we have no control over. You can possibly do something by increasing the heat input out there, but the consequences are difficult to understand. And diametrically opposite schools of thought as to what would happen if the North Atlantic sinking of this cool waters ceases because of global warming. You can have very unpredictable results. It can swing either way. But what is of interest to us out here is the part that lies here between the inertial period and the global thermohaline circulation. You have eddies on the smaller scales. You have planetary waves, and you have large-scale ocean circulation. And it is this part that I will be looking at in the rest of this talk. Okay, consequences of the scale and the rotation. Low aspect ratio, you have low thickness compared to length, and it leads to the hydrostatic approximation being valid. What it means is that if a parcel were to rise from the bottom of the ocean to the top, and this change were to take place across the length of, say, the Arabian Sea, at 15 knots, the vertical movement will be a few kilometers, but in the horizontal, the movement will be a few thousand kilometers. So if you were to scale the velocities associated with this motion, you would get a velocity scale ratio that is similar to that of the densities. So vertical velocity in the ocean tends to be very small. In fact, there is no way to measure it directly. It's always inferred as the residue. Which means that in the laws of motion, when you look at the vertical momentum balance, it just scales out. So it turns out the pressure gradient balances the weight. So dP by dz is minus rho g. That's the hydrostatic approximation. That's one major consequence. There's rotation which we cannot ignore. And I told you we're going to be looking at periods greater than a day. We're not interested in periods of the order of 10, 15 days. We're looking at what's called the seasonal cycle. Implies the dominance of the Coriolis acceleration, something we cannot ignore. And one remarkable consequence of that is that waves dominate. You can do a complete course in engineering fluid mechanics, whether it's aerospace, mechanical, or civil, and not look at waves at all, except shock waves, which are a completely different kind. You don't have to look at it. But in geophysical fluid flows, from the word go, you have waves. Because that's omnipresent. No matter where you go, you look at nature, waves. It just strikes you. Coriolis force is a funny kind of force. It acts only when there is motion. So if this parcel moves, Coriolis force acts. Ceases to move, Coriolis force goes out. It leads to two kinds of balances that we look at. One is called Ekman flow, where friction balances Coriolis force, and the other is geostrophy. pressure gradient analysis Coriolis. So this is basically a scaling of the momentum equations. Depending on what you're actually seeing, the phenomenon you're studying, you scale the momentum equations and you get two kinds of balances that have dominated much of oceanographic literature. What is Ekman flow? Suppose you have a tank, flat tank, and you put a sheet, a thin sheet, an aluminum sheet on the surface. Okay. So you have a tank like this, and let's say I put a sheet on the surface tangentially from right to left. Which way will the water move? Which way? I have to be able to hear. Same direction? Is that okay? Okay? And you carry this out in your bath with a tub. You just take a small sheet, just put it on that, and it will move in the same direction. Right? In the ocean, it turns out that's not what happens. And you have a sheet that is being pulled all the time, that's the wind. So it's the wind blowing on the surface. The trouble is, the moment the wind blows in this direction, the Coriolis acceleration comes into play because there's water in contact with the wind, the surface. It moves. The moment it moves, Coriolis acceleration comes into play. And Coriolis acceleration, if you look at the map, is directed in an angle to the applied force because there's a k cross. K is the coordinate outward of the sphere. If you were to open the Earth out into a flat plate, it is the vertical vector. So you get a k cross. So if you have a velocity vector that's pointing towards you, k cross will go in this direction. So the moment the wind blows on the surface of the ocean, the water goes off at an angle. The trouble is that this is going to be only at the surface, but that layer that moves now imparts the momentum to the layer below it through friction, because there is an exchange of molecules, or in this case, small eddies across these so-called layers, which are artificial. That gets pulled, and then the moment it moves, Coriolis acceleration comes into play. And the fastest moving layer is going to be the one in contact with the wind, because that's the one that's directly driven by the wind. The velocity will increase as you go down. So the Coriolis acceleration, which is directly in proportion, the velocity will also decrease as you go down. So the angle keeps changing, and you get a balance between the wind and the Coriolis acceleration. So the wind blows. It deflects the Coriolis acceleration deflects the current, and if you track it, you can get spiral. So at the depth of frictional influence, it's called the depth of the Ekman layer, given by D here. The current is opposite in direction to that of the surface, and its value has gone to 1 by E of that of the surface. This spiral, unfortunately, is rarely seen in nature. Very rarely seen in nature. Because the conditions under which Ekman derived this equations normally don't hold in the oceans. One of the major assumptions made is that there's no horizontal pressure gradient. It's a condition that's literally neutral. Now, Ekman's theory was, paper was published in 1905. It's the same year that Ekman published his paper on boundary layer theory. In 1904, the year before that, Mantle had given his lecture in Göttingen. But practically the entire development in boundary layer theory was to come from the laboratory. Because measurements are very difficult to make in oceans. So the details of the spiral are very difficult to observe. We do have some data that show that here it does change direction and you get some kind of a spiral. But the other part of Ekman's theory does hold, which is that if you were to integrate the velocity over the depth of this Ekman layer, the transport is at right angles to the wind. So if the wind blows from right to left, the transport in this Ekman layer will be towards you. Right angles to the right in the northern hemisphere. In the southern hemisphere, the Coriolis acceleration changes sign and it will go to the left. Okay? So this is one remarkable difference. If I pull a sheet on the surface in the laboratory, the flow is in the same direction. In the ocean, it's at right angles. The other one is quite justified. Let's go back to our tank. We now draw a wall, put a wall in between separating the two parts. So we have, say, more water on the right, less water on the left. I remove the partition, like a dam. I just remove that partition. What happens to the water? It just flows down the pressure gradient, right? Minus gravity, because the gradient of pressure is from left to right. It just flows down the pressure gradient. The trouble is that in oceans, the moment that happens, Coriolis acceleration comes into play. It deflects the current vector to the right. And the balance that says occurs when the Coriolis acceleration, the Coriolis force, balances with the pressure gradient force. So if I have a sea surface that slopes up from left to right here, then the pressure gradient force is from high to low, sea level, but the Coriolis force goes the other way, the balancer, and the flow in this case is into the wall. So in the ocean, if I were to tilt the surface like this, in the northern hemisphere, the flow will be towards it. Okay, so these are the two major balances that are of interest to us. One is Ekman, where the wind stress balances friction, Coriolis acceleration. The wind stress is basically friction. So it's a balance between the friction stresses and the Coriolis acceleration. In the other case, you have geostrophic, which is the balance between the pressure gradient force and the Coriolis acceleration. And it is here that you can see why those temperature profiles might be useful. So let's move on. It turns out that sea surface interior is useful, but not all that useful. That's because of stratification. Now, if you were to look at the kind of flows that occur in the ocean, you take tides, for example. You measure the tide at somewhere in the middle of the ocean, you will find a few centimeters. That's oscillation. Today, you can measure that kind of oscillation with a satellite. Many reasons it's practically impossible unless you had an island station where you could put a tide gauge. Near the coast, the tidal amplitude increases. But those flows are what are called barometric. In that, if you were to look at an isobar, it slopes up at the same angle, no matter where you go down. So if you have an angle theta of the surface, you find the same angle as you go down. But the ocean is stratified, and the kind of flows that we are interested in are essentially driven by the wind. And the wind portion is momentum at the surface. Its direct influence decays by the time you get to the depth of the Ekman layer. But an indirect influence, because of the pressure differences that are set up, can be felt much deeper down. But even then, it will weaken considerably as you go down, deeper and deeper. So there comes a point where you could say that the influence of the winds has decayed to a point where you could consider that isobar to be practically horizontal. So if I do that, then I make all my pressure measurements now with respect to this isobar. And I have the hydrostatic approximation. dP by dz is simply minus rho g. So if I move rho by some means, then I can make a measurement all the way up and I can get the surface. The moment I get the surface, I get the current because of geostrophy. It is in this context that those temperature and salinity profiles are available. You have what is called a level of motion, a reference level with respect to which you can make your current estimates, and it works basically because the major forcing is the wind and the impact decreases as you go down. This level of motion in the avian ocean is typically taken to 1,000 meters, but it varies depending on the problem you're studying. So suppose I have two profiles at A and B. I get the density here, I get the density here. I just use the hydrostatic approximation. I can determine the pressure fields relative to this pressure, and that is constant because this is the isobar. So this pressure is the same at A and B. So with respect to this level, I can know what the current is above it. But what do I get? I get the average current between these two profiles that I have collected. So the two major sources of information on ocean circulation are the shipwrecks, which are not today because of satellite navigation, and you can correct your course every few minutes, and you can even do it automatically through the kind of computing systems that we have on board modern ships. And the other one is these temperature and salinity profiles. They're still being collected. Okay. There's one other question that we have to answer. One question I have to answer at the end is why I'm not bothered about that slope. I hope to justify that by the time we end this two lectures. Why are we looking at everything else but not bothered about the slope? The other is if you were to look at the tide itself. This is an actual tide record at Apollo Bunker, which is at Mumbai. Apollo Bunker is remarkable because if you look back in time, it is one of only 3 records in the tropics, between the tropics of Cancer and Capricorn, that extend back over a century. The other two are Angola, Panama Canal, it's almost equatorial, and the other is almost not tropics, Honolulu in Hawaii. Just makes sense in the tropics, pretty close to the Tropic of Cancer. So Apollo Bunker is a century-long record. It dates back to 1878. And this is the tide. The vertical axis, the data is in centimeters. It goes from minus 250 to plus 250. And what you see here is 16th of May to 15th of June of a particular year, 1976. So these are data that are collected every year automatically. So what is plotted here in red color is just the water level. And the tide range at Apollo Bunker is almost 5 meters. So if you were to set the Apollo Bunker over the course of a day, it goes up and down by 5 meters. It has implications for several meters. In Mumbai, the entire sewage disposal system depends on the tide. You have a city that was built on a palace. And the sewage disposal system goes under the water level. There is nothing you can do to push the water out of the sewers during tide coming in. You have to wait for the tide to turn before you can send that water out. Which means that if you have a heavy rainfall event, that's happened in 2005, not sure, 2005 perhaps, July, about 100 centimeters, close to that in a day, you still stand a ghost of a chance. Nothing can be done. Because the tide comes in and goes out twice a day. It's a semi-annual tide that comes at Mumbai. There's nothing you can do to flush the system. The water will accumulate until the tide goes out. That's when the water levels can decrease. The sewage system collapses. What also collapses is the drainage network. You can't even drain out that. Where will you flush it? But anyway, the tide is of order 5 meters. I take this RV data, I average with running mean, 24-hour running mean, and that's this blue line drawn on top of that. So that blue curve is plotted here, 16 May to 15 June. But now the auditing has changed, it goes from minus 40 to plus 40 centimeters. And what you see over here is a small blip on the tide chart. There is the storm surge that occurred in Mumbai on the 1st of June, 1976. That's of the order of about 25 centimeters. It changes the sea level by 25 centimeters. You don't want to see it that much in a 5-meter tide record. Near the 5-meter tide Apollo Bunker, you have to build your structures to handle that daily change. So your factor of safety will be much more than this. The storms are not that critical. Now we look at the whole of 1976. This is the whole of 1976, the blue curve plotted again. And this is the storm surge. Beginning of June. But just as we went from RV sea level to daily sea level, we can go from daily sea level to monthly sea level. That's the red curve. Superimposed out here. For 1976. Which has been replotted here. This is now minus 20 plus 20 centimeters. So the red curve is for 1976, a particular year. And the range is decreasing. This is monthly sea level. So if I'm looking at the seasonal cycle of sea level, it is the kind of data I will be using. The storm surge is of no consequence anymore. The blue curve is what we call as climatology. You take all the Januaries that are available, and there's about a century of Januaries, average, and that's what you get. You can do that for each of the months. So the blue curve is the climate signal of sea level. It is what you expect in any given year. If you say I expect a certain monthly sea level in Mumbai, this is what you expect, what's given by the blue curve. What you get in any given year is the red curve. This red curve is for 1976. The average one, just as we went to monthly sea level, I can take those monthly sea level data, average them over a year, and that's about it. The red curve here, it goes from 1875 to 2000. And this plot was made in the late 90s, and the data stopped at 1988. In those days, the data used to come with a 10-year lag. So what you see here in the red color is the annual sea level, and the ordinary exchange goes from minus 10 to plus 10 centimeters now. So you see changes in annual sea level. The blue curve, superimposed on that, is the 10-year running rate. So you see low sea level from about 1875 to 1925, and it increases with the peak around 1960, then it decreases till 1990, and it increased again after that. So if you were to fit a straight line, you miss the entire set of signals that are embedded out here. And there's no way to interpret that straight line without understanding what this curve is. Because the straight line fit depends on where I'm looking. If I look here, I see a slope that is very high. If I look here, I see a very different slope. And tide gauge records vary in length. Only record that is a century long in the Indian Ocean is in Mumbai. So when you talk of global sea level rise, in particular for the tropics, you only do useful stations when you talk of long term. Balboa and Panama and Mumbai. There's nothing else available. All of the records are varying lengths, maybe 40, 50 years. And we are looking at some part of the time history. That has to be kept in mind when we draw those straight line fits. Okay, the other question then, why do we have to study this noise at all? I mean, these are just noise, 10 centimeters in a signal that is 5 meters. Why do we even bother about it? The tidal range is about 4 meters. Storm surge range is 40 centimeters. You can understand its importance. Inter-seasonal variability, that is this blue curve out here, it's of the order of 20 to 40 centimeters. The seasonal variability given out here is of the order of 20 centimeters. And we have interdecadal variability. Again, the range is of the same order, 20 centimeters. Why do we even bother about just playing 20 centimeter changes when you have a tide that is 4 to 5 meters? And why do we care at all about these things? The answer lies in the same old thing, stratification. If you look at a typical density profile in the oceans, this is the kind of short dashed line, not a line. This is what you find in the polar regions. What you see here is the tropics, and then you have the mid-latitudes. So this is the tropics and this is the mid-latitudes. But if I were to try building a model of the ocean, the simplest model I can possibly get is one in which I look at this density barely changing over the bulk of the depth of the ocean. How do you change this? So I approximate that to be a constant, and I take the surface density, I approximate that to be a constant, and I collapse this entire region where the density changes from what you see at the surface to this roughly constant value out here into a point in the vertical. So this region where the density changes, called the Picno line, in temperature, if you're looking at the temperature profile, it's called thermocline, is collapsed into a point in the vertical. So I have a two-layer ocean with density ρ1, which is less than density ρ2. Ocean is stratified, and the difference in density ρ2 minus ρ1 is much smaller than ρ1 or ρ2. ρ1 is almost equal to ρ2. Density of water is what is seawater. Look at very well approximated in any of these models with 1000 kg per meter cube. It will change the number just a little. But the difference in density is small. And it turns out that because of the stratification, if you see a change in sea level that is given by, say, eta, then the change in any of these isotherms or isotherms is much larger. So if eta is the difference in sea level between this point here and this point, then the change in the depth of isotherm between these 2 points is of the order of rho divided by ρ2 minus ρ1. In other words, sea level eta is delta rho, the difference in density, divided by rho. And if I say rho is 1, then it is second or third decimal place change, that is delta rho, multiplying this difference in height. So though the sea level change may be of the order of 10 centimeters, the change in these isotherms is of the order of tens of meters. So if you have an outer layer that is of the order of 50 meters thick, then the change of 20 meters in the thermocline is not small. It's 40% of that height. That top layer is what the atmosphere is seeing when you talk of weather or climate. It is that plate on the surface that's coupled with the atmosphere. Sea surface temperature. There is a difference in the thickness of these plates. It changes over season and in space. So it is because of this difference that we study the noise and ignore the signal in the rest of the structure. This sea level signal was not measurable in the open ocean except at island stations before the satellite era. But today you can. But when we are looking at that sea level signal from the altimeter, our interest is not so much in the sea level itself. Our interest is in the indication of the thermometer. That is why it's good. Okay, so what is the theoretical framework? This is a map of sea surface temperature. It's climatology from the atlas of Divecha. And you have, as you would expect, warm waters in the tropics and cooler waters near poles. This again is a picture from school textbooks. You have the equatorial low pressure system, you have the subtropical high pressure system, and wind blowing from the high to the low pressure, deflected to the left in the southern hemisphere, deflected to the right in the northern hemisphere. Convergence at the equator, and therefore air rising at the equator, then it moves out towards the subtropics and sinks out there. The sinking air generally coincides with the great deserts of the world, and the rising air in the equatorial lows implies you have almost daily rainfall in the equatorial regime. This is the Halley situation. You have the circulation here, that's the paracel, and you have the polar cell. We're not worried about that. What is of interest to us here is the winds. You have the northeasterly trades and the southeasterly trades. Fairly steady winds. And they converge towards the equator. So if you look at climatology of rainfall, you can see that you have equatorial peak in rainfall, the shift of the equator, it doesn't concern us here. And it decreases as you go away. And we are very low rainfall in this regime where the Hadley cell descending branch lies. So this winds and rainfall in March, which is the equinox. You have the high rainfall band sitting near the equator. It moves in time. You have movement towards the south following the sun in January, and in July it moves towards the north. These are two diametrically different views of the globe in two different months, but basically showing the same thing. Okay, now we are trying to explain the subtropical currents, why they exist. We are trying to explain why the boundary current is at the western boundary, not at the eastern boundary. Why is the river flow extending all across the basin? And why does a large part of the river flow right at the east of the boundary line itself? So these are the 4 things we want to explain. And it was a remarkable 5-year period following World War II that the explanation was found. The first one came in 1946 with Harold Sverdrup, after whom the unit of transport is named. Sverdrup made one dramatic departure from what Ekman had done. Ekman had dropped the pressure gradient time, and he had retained the vertical structure. That's why he got the spiral. He got basically a boundary layer solution. Sverdrup retained the pressure gradient, but in the process of simplification, he had to drop something, and he decided to ignore the vertical structure. So the transport that he got is the sum of both Ekman and geostrophic flows. So the details are gone, but there's something else that he can get that Ekman could. He approximated it to a first order equation. A first order equation in case. If you have a first order equation, you can have only one boundary condition. That's all you need. And that's all you can have. The solution was remarkably simple. It's just beta V equals curl of tau. Tau here is actually tau by rho. Rho has been absorbed into tau. Tau is the wind stress. So on the right hand side is the curl of wind stress. Beta is the rate at which Coriolis acceleration changes with latitude, the beta curve. And V is the melting of velocity. Now, if you look out here, what you find is an anticyclonic curl of wind stress. Tau is negative here and positive here. You have the trade winds, and all we are looking at is the zonal component of the trade winds. Likewise, we are looking at the zonal component of the winds to the north of the trades, that's the westerlies. So the westerlies are positive, they go from west to east, the trade winds are negative, and you calculate the curl, you get a negative curl of wind stress, anticyclonic curl. So curl tau is negative, beta is positive, and V therefore is negative. So there's negative anticyclonic curl of wind stress, and it forces a gentle equator pressure all over the basin. The western boundary transport then is the transport that is required to balance the mass, close the circulation. Now Sverdrup had a first order equation. So he could integrate either from the east or from the west. He looked at the data and decided to integrate from the east. Mathematically, there's nothing that tells you which way to do it. He just decides to do it from the east, and therefore the boundary current appears at the west. If you were to integrate it the other way around, you would get the boundary current on the other side, on the eastern boundary. Both are equally valid in this type of solution. What fits the observation is the integration starting from the east, and that's what he does. He applies the boundary conditions there. So, since we have a first order equation, he explains only one part of the problem. Why is there this equator flow over the bulk of the subtropics? That is explained. And the boundary current is simply what is required to close it. Balance the mass. The next paper was 1948, Henry Stommel. Stommel carried out 3 experiments. The first one was with a non-rotating Earth, and he got a nearly level sea surface. The second one had a constant Coriolis acceleration. So now he got a higher sea level around which there could be flow. But the high sea level, as you would expect from symmetry, is at the center of the basin. Here's a rectangular basin. This high sea level is now at the center of the basin. He has no way to explain why you have a boundary current and the equator would flow over the rest of the basin. The moment you throw in the latitudinal variation in Coriolis acceleration, the beta effect, you got the westward intensification. The boundary current shifted to the west, and there was an equator but flow right across the rest of the basin. So the beta effect, when used by Harold Sverdrup, explained the equator but drift, but he had a first order equation. Stommel solved it differently. He included what's called bottom friction, and by doing that, he could get a solution that would allow him 2 boundary conditions in X. And the moment he got that, with the beta effect, he got the boundary current shifting towards the west. So it's this change in Coriolis acceleration because the Earth is a sphere, and the rotating sphere bringing the Coriolis acceleration, the spherical nature bringing in the beta effect. that shifts the boundary current to the western side. The next paper was in 1950 by Walter Monk. He had a more realistic wind forcing. He had a fourth order equation. He put in Laplace and friction. And the moment he did that, he could satisfy two boundary conditions in X on either boundary. You have a fourth order equation, so you need four boundary conditions in X. So he has no slip as you normally apply in fluid flows. The solution allowed the counter current to exist just east of the western boundary current. That's some observations. So in this 5 years following World War II, 3 remarkable papers changed the face of technology. The observations had started about 70 years back with the Challenger expedition, 1870s. And the explanation for what the Challenger expedition saw and later observations confirmed these gyres, the semi-permanent subtropical gyres. The explanation had to take almost several decades. So what's the summary? Geophysical fluid flows are different from classical fluid flows. One reason is the low aspect ratio. We're talking about very thin fluids. Another is sphericity. You cannot ignore it when you're looking at flows that encompass practically the globe. And rotation. Again, you cannot ignore it because you're talking of phenomena that have time scales greater than the time taken by the Earth to spin on its axis. Stable stratification in the oceans. This is an important thing. It makes our life much easier than it is in the atmosphere. The global ocean circulation is characterized by semi-permanent subtropical gyres and intense western boundary currents. These are steady-state solutions. Sverdrup, Storm and Mount. These are steady-state solutions. They are forced by the curl of wind stress in the interior of the ocean. Interior in the sense of the horizontal, away from boundaries. Sphericity and rotation implies strong currents at the western boundary. So that's as far as the global ocean is concerned. And this theory can explain the basic features of the circulation in 5 basins. The one that is left out is the North Indian Ocean. And that is because of very different kind of winds that you see out here. So before I go on to the North Indian Ocean, is there any questions we take them here? It's been a monologue so far. Okay. This is the seasonal variation in IISc. We're going to see this is January, when sun is farthest south. In May, when it has crossed the equator, it is moving towards its northern limit that comes on the 21st of June, and this is in July. You see two things here. One, the band of long IISc moves farther north in the Indian Ocean than this part of the Pacific than it does anywhere else. The other thing to note is the asymmetry. The western part of the Indian Ocean is cooler than the eastern part. This is rainfall and winds. So you have the rainfall concentrated out here, close to the equator in Jan. And in July, it's moved much farther north in the North Indian Ocean. This movement of this rainfall band is maximum over the Indian Ocean. It has gone over the Indian subcontinent. Nowhere else in the world oceans you get this kind of dramatic change. The moment you have rainfall out here, it implies that you have clouds. You have condensation in the middle of the troposphere. So you are establishing a monsoon pressure gradient in the middle of the troposphere. Suddenly, you have over the day, these are the southeasterly plates. They cross the equator and they blow in from the southwest across the North Indian Ocean. This is not something you find in the other oceans. You do get a seasonal migration of the convergence zone, tropical convergence zone, but it's nothing compared to what happens out here. The complete direction has changed from northeasterly plate-like winds to southwesterly winds. And this makes the North Indian Ocean very different from the other 5 basins. It's the only basin for which you need to show more than one picture to describe the most significant feature of the wind field. So that's what's done. These are anthropological data from Josie et al., Southampton mythology. You have the winds in January, and this is only from 5 south northward. So you have the northeasterly winds. In March, the winds have collapsed. They're very weak, transiting towards the summer monsoon. By May, the winds are reversed to blow from the southwest across the Arabian Sea and the Bay. In July, the winds peak. They weaken by September, and by November, they have started reversing. So there's a very strong seasonal cycle. If you were to compute the mean wind, it is much weaker in comparison to the seasonal cycle. This is the key difference. In the other basins, the mean is the dominant. Harmonic. The frequency that dominates is lowest, that's the mean. What happens here is very different. The dominant frequency is that associated with the seasonal cycle. There's one more thing that's of interest out here. Because when you look at a wind that is changing like this, we need some focus, otherwise we're going to lose our ground. I have 3 hours in which to take you through this whole story. So we're going to be focusing our attention on what happens around the Indian coast. We're not going to worry about the entire basin, just kind of look at it. Now, this is an excellent of geography. Look at the winds. You see bigger winters in the Arabian Sea, July. That's the Prelude jet going across the Arabian Sea out there. The mean winds for July are weaker over the Bay of Bengal. But if you look at the longshore component, and this longshore component is important because of this Ekman flow and geostrophy. If you have a coast and you have a wind blowing like this away from me, the Ekman trend will be away from the coast in the northern hemisphere. We are looking only at the northern hemisphere. It goes away from the coast. Conservation of mass demands that water will be dried up. Right? That's a fact. So here we will at the coast the thermal can be true. If the wind were to reverse direction and blow the other way, the transport of mass taking flow will be towards the coast, which means thermal can will go down, sea level will rise, and you will get a geostrophic current that goes along the coast as a consequence of that, because there is a offshore pressure gradient capacity. Okay. And what is of interest are these longshore currents? If you want to know the longshore current, you need to know the cross-shore pressure gradient. If you need the cross-shore pressure gradient, you need to get your rate and flow right, for which you need to know the longshore wind. That is the important thing. What is important is not the strong pendulator jet. That does other things, we are not worried about it. What is of importance for the west coast of India is the longshore component of that pendulator jet. And likewise, what is the longshore component of this southwesterly wind in the Bay of Bengal? This is an accident of geography. The east coast of India is aligned with the wind. So if I decompose the wind into longshore and cross-shore components, most of it contributes to the longshore in the Bay of Bengal. In the Arabian Sea, on the other hand, if you were to decompose the pendulator jet near the coast, most of it goes into the cross-shore component. So you get a much bigger longshore component than you do on the east coast. The other thing that happens is more intriguing. On the east coast, the southwesterly and northeasterly winds, they reverse direction. But while you have a gentle reversal of the wind over the Arabian Sea here, northeasterly is here, and southwesterly is here, if you look at the longshore current, it is unidirectional. It always goes from pole to equator. The longshore wind is unidirectional. It doesn't change direction with the season. If I were to plot the longshore wind of Shankar out here on the east coast, I get positive wind that is southwesterly part over part of here and northeasterly is over the other part, negative. While if I were to do the same thing abroad, there is a change in magnitude for sure, but the direction does not change. Okay, this is the only thing that you have to keep in mind. The direction of the west coast does not change in time. Okay. So what is the observed surface circulation? Make a shift of wind. And unlike earlier, where you would just show one picture and get it, you need 6 to start telling the story of the North Indian Ocean. Again, we're not going to worry about all the details. There are very interesting features, there are many things to study, but we'll look at the coast of India. Generally ignored by many, but As I'll show you towards the end of this lectures, if you ignore the coast of India, you cannot understand anything that goes on in the Northern Ocean. Nothing can be understood. Okay, now in July, the wind current along the west coast of India, it's called the West India Coastal Current, is towards the equator, the longshore current. So it's in the direction of the wind. In January, however, it goes the other way around. It flows into the wind. This is something we would like to explain. Why does the current flow into the wind? And it turns out to be the stronger of the two currents. The other thing that is of interest is what happens on the east coast of India. You have a onward current that sets in by February, it peaks in March, April, still there in May, it weakens actually in July, starts reversing in September, and in November you have a flow that is towards the equator. So this current would be almost straightforward, and for a long time it was put down to being driven by the longshore wind, the local wind on the east coast. But the catch is that when the winds peak along the east coast, that is in July, the current is not all that strong. The strongest current on the east coast of India is actually in March, April, when the winds are at their lowest. This is the other thing we would like to explain. One thing we are interested in is why does the West India coastal current flow into the wind in winter? And the other thing we are interested in explaining is why is the East India coastal current weaker in July when the winds are at their peak compared to March, April, when we have a very deep wind field over the entire basin. This picture is something that oceanographers have been able to see only after the satellite era started. Satellite altimetry. This is from Protexpo site. It is basin by sea level field. Red colors mean higher sea level, which means the thermocline goes down, so you have a thicker mix layer. And the blue colors imply sea level dropping, so you have a thinner thermocline, thinner mix layer, thermocline coming up. So you see patterns out here that are remarkable. For example, if you look at this low in sea level in green color, you find that it spreads. It spreads westward. It's replaced by high in sea level out here in January, and that high also spreads westward. Likewise, you have the organization of circulation in the Bay of Bengal. Now, these are basin-wide patterns that were theorized. Theories said that they have to exist, but there were no data. We don't have any islands in the Indian Ocean, practically none, unlike in the Pacific. The equally Pacific currents would be mapped because of tide gauges. There were currents that were predicted by theory, and it was tide gauge data that actually showed how the currents behave, because there are islands in the Pacific. In the Indian Ocean, there's practically nothing. Between the Andamans and the east coast of Africa, you have nothing. And out here, the islands even come pretty close to Somalia, so there's nothing available to measure anything in the middle of the basin. This kind of picture has been available to us only since the mid-90s. I'm just going to go quickly through this. You have a high in sea level out here, and you will see it spreading westward with time. And you can see an Indian geostrophic current that flows around. This is the West India coastal current, it's reversed by May. Out here it is still flowing forward in the bay. The strongest current in the bay is in March, April of the east coast of India. By June, the current is actually weakening in the of the east coast. In July, it's still there, it's still flying forward, but it is quite disorganized. And in September, it starts reversing on the northern end, and then it flows down over the south by November. And then it starts reversing again in December. So this is the kind of circulation we have. Now, 3 maps is all I'm going to show you based on what we knew before the satellite era. But one more thing to remember is that the satellite gives you a roughly synoptic picture. Synoptic in the sense of a repeat cycle every 7 days. The trouble is that it cannot show you anything below the surface. There's no information available from anything below the surface of the ocean from satellite data. So it's good in time, but terrible in the water. These kind of pictures is all that oceanographers have based on temperature and salinity. You conduct cruises maybe a month or more long, and these are typically conducted in different years. You go on a cruise, you digest the data, you go out some other time, you again require some time before you can go out again. So you are conducting this cruise in different years. That has to be kept in mind. And we saw that the sea level patterns change from year to year. At least the tide gauges show that. So if you go in July this year, and you go again in July next year, you can expect things to be somewhat different. There's variability from year to year. But you don't have data every month in every year. So it's queer kind of climatology in the sense that when you have such cruise data, you tend to think of them as representative of what is happening out there. Now this is a drawback, but it has to be understood properly. When you have sparse data sets, you have to exploit them to the best that's possible, keeping in mind the efficiencies. So the East India coastal current in winter flows equatorward with a transport of 5 to 8 Sverdrups, and the Poleward West India coastal current is about 7 Sverdrups. The most famous current out here is the Somali current, and that's of the same order. In the spring winter monsoon, that's around March, April, the West India coastal current flows over the central and northern parts of the west coast, but it flows equatorward over the southern part of Kerala. The transport is of the order of 3 Sverdrups. East India coastal current during the speed of 8 minutes is 10 Sverdrups, and this is the 1,000 meters integrated away from the coast towards to the extent offshore limit of this current. And 10 Sverdrups is not small when compared to the Somali current, because the transport associated with Somali current has been estimated to be of the order of 20 Sverdrups. So these East India and West India coastal currents are not that small. You're talking about roughly half that in the Somali current system, or half that of what is associated with the Whitley jet at its peak in March, April. That's again of the order of 10 to 20 Sverdrups. We're talking of current systems that are not trivial. In July, if you integrate all these India coastal current, you get just 1 Sverdrup. So the winds are at their peak, blowing along the coast, you should get a strong current. You don't. It's the transport is just 1 Sverdrup. And this is something that we would like to explain. Why is this so? You look at the hydrographic data. We saw one of the Gulf Stream, and this is for the east coast of India and the west coast of India. Now remember that it is the east coast winds, longshore winds, that are stronger during the summer monsoon. So this is from a particular cruise that was conducted in 1989, paper is dated 1991. This is the coast, the topography, and you have an isotherm coming off very, as you would expect, because the wind is blowing poleward along the coast. The Ekman drift is offshore to the right, and water has to come up. So these isotherms come up. Off the west coast of India, again you have the wind blowing all through the year towards the equator, pushing the water offshore, upwelling water. Now the longshore wind is stronger off the east coast, but you look at the isotherms, they are very much less than on the west coast of India, where they have much weaker longshore winds. Why? It's clear that there must be something more than just local winds that are determining the circulation. Once again, the same picture. Near a coast, if you have the wind blowing into the coast, that's on the left. The Ekman transport is into the coast, sea level rises, the thermocline or technocline goes down, that's supposed to be downwarding. If you have the wind blowing out of the boat, sea level goes down, and the thermocline or technocline comes up because the transport is offshore, that's coastal upwelling. So what's the theoretical framework? One need to break up, and we come back after the break. It's just short of 11. I don't want to stop this halfway, and there are quite a few slides out here. 2 slides and then we will call it quits for the first half. Now, when you try modeling the circulation as you would do in computational fluid dynamics, you break the basin, in this case, into boxes. This is horizontal. You have X coordinate as the longitude, your Y coordinate as the latitude, and in the vertical, you have to ensure that you resolve the surface part much better than the part below, because density change is much less in the vertical once you are below the normal. While it's at the surface that you start seeing much more rapid changes in the vertical. So your model has to be on that. So you generally have more levels in the vertical near the surface, and the spacing between the levels increases as you go down. What would be a resolution depends on what you are studying and what's the kind of computer you're on. So the model portion is divided into stacks of boxes, and it solves primitive equations, which are a version of Navier-Stokes equations, but with the coherence explanation included, and 2 approximations invariantly made, hydrostatic and basins. The differential equations are solved in finite difference form, and most towards that you get, irrespective of the time of model you pick, is generally 4190 or one of its variants, more modern variants. So this is typically what you will do. The point is that if you look at this kind of a model, you do get a solution. You can compare it with observations. Sometimes pretty easy, sometimes not so well. But when you solve a complete set of equations, even if you succeed in simulating what you are seeing, you don't know why you got it right. And when you go wrong, you don't know why you went wrong. That insight into phenomena is different from an academic simulation. Insight comes by breaking the problem into pieces and looking at it from different angles. If it was not for the kind of simplification that Ekman had laid, inspired by boundary theory and one observation, a friend of his, Manson, a biologist, had gone sailing in the Arctic, and he saw that the iceberg was drifting at an angle. It was not going with the wind. It is just that one observation that Ekman had in Quantum's boundary theory, perhaps. And he built an explanation, but he made approximations. If you were to look at the Navier-Stokes equation, throwing the coherence acceleration, you would have had a very grand set of equations, but you would have done nothing with it. It is that ability to drop terms that leads to progress. And this was the remarkable change that Ludwig Prandtl brought about. You have, till then you had inversely flow theory, but you know that there is a drag force associated with the flow over a plate or over a magnet. You know that when you have a flow and you have enough bodies in the flow, there is a drag force. You can see it moving. You can see that the bend because of the force associated with that drag that comes in. The trouble is that without friction you cannot calculate that. And if you include the friction in the Navier-Stokes form, you can't solve the equations. You have an organic system with second order friction between the two of them to make life almost impossible. What Prandtl did was to show that you could simplify the equation within the boundary layer. So outside the boundary layer, you solve violent equations. It is still not in aerodynamics. You solve, even for objects, you solve the Boltzmann equation near the cone, where you have a shock wave and you have very high temperatures. You solve the Navier-Stokes equation in some part. You solve the boundary layer equations and the rest of the boundary layer regime. And you solve the boundary equations of everything. This was the remarkable thing. Practically all progress depended on this. And the same thing happened with Sverdrup. He couldn't explain everything, but he made some remarkable assumptions. He retained the pressure gradient, was willing to lose the vertical structure, and he could explain one aspect of the observation. Why is there equator drift over practically the entire basin? He also knew which way he had to interpret. And mathematically, there was no reason a priori to go from east to west or west to east. You have a first order differential equation. Mathematics will never tell you that. It is an insight into phenomena that does that. So these kinds of models, while they are remarkably successful at times in making predictions, and if you want to predict weather or climate, it is these kind of models, general circulation models, that you use. The trouble is, insight is a problem. So, I mean, you look at circulation equation or GCM, this is the modular ocean model, probably the most popular of the models used in India. Look and see that, if you recall the observation, if you look at the circulation pretty well, this is 35 meter current. The circulation is made by Professor Vinay here. Unfortunately, he is not around today afternoon. You get the increasing the coastal current doing exactly what we expected to. It's strong in March, April, it's weak in July. You get low transport in July, you get strong transport in March, April. You get the West India coastal current flowing into the wind in January. You get everything reasonably right. Instead, I will tell you why each of these things is happening. For that, you have to break that problem into pieces. And the major problem here is nonlinearity. So that's the next thing we look at. We need insight, and that's the game we are playing. We are not happy just to be able to tell what will happen. We also want to know why it's happening. Just as we were not satisfied by just describing the constraint. It doesn't change direction, but why? Why does the Somali current flow the way it does? Why does this East India coastal current or West India current coastal current behave the way it does? And unless you understand, you will not know when your prediction is valid and when it is not. So that is what we will do when we come back.